Right now, it's not that dense yet at the audience, but we will be waiting for you. So this is a moment for me to give you kind reminders. Please make sure to download the conference application if you still haven't. So this is also a communication means, so you can use it to ask questions right there, or you can speak up via microphone if the Q&A session is foreseen and is actually embedded. Those shorter lectures, they will not be given a chance to go Q&A. Those longer ones, as we could see before the break, they had them. I was also asked to remind you also about the actions, those challenges, riddles, and contests which are ongoing in the corridors of New Horizons Cinema. Yes, they are. There are also attractions. So the VR, please try it. I just said I quit. I couldn't make it. Sorry. But it's really nice, by the way. And you can also rate the lectures, which are either inside room 1, 8, or 9, wherever you went to. Just please make sure to give some feedback. It gives some positive, negatives, but we collect this data, and thanks to that, Nokia can make this conference even better, which I would like to thank you in advance for doing that. Okay, and finally, there is the after party at 7:30. I will be repeating this fact once again, and I will give you some details regarding that later on, but please remember 7:30 p.m. After a party, Code Dive, yeah, that's just it, in Wrocław. Okay, so I think we can try to switch to the next one. We are just in for the contract assertion against security, functional safety, and correctness, to be presented by Andrzej Krzemieński. But as we agreed, we would be presenting some fun and facts about Wrocław, but actually this one is going to be a more general one, I believe. If someone is from Poland, please raise your hands just for a moment. Quite many of you, but for those who are not, I will explain. We are really fans of beetroot soup right here in Poland. So Wrocław's obsession with barszcz and pierogi is actually very known, not only in Wrocław, but Wrocław as well. So while pierogi are popular across the whole country, Wrocław has a special love for barszcz z uszkami, which is the beet soup with small mushroom dumplings, mostly taken over from the eastern parts of Poland, which were brought with the history right here at the end of the Second World War. So by the way, it's a very Christmassy dish, but we tend to eat it as well throughout the year if someone wishes to, of course, and that's exactly how it looks like, and we really like it. We really like it, especially spicy and sour, at least in my case. Okay, but now it's time to present the next lecturer or speaker, however you name it. Andrzej Krzemieński. So he has been a software developer for over 21 years. He works mostly with C++ in commercial software, which includes safety-related and high-performance systems. He's a member of the C++ Standards Committee and a Boost developer. He's also a co-organizer of a C++ user group, Kraków, known to the community, well, probably for his wide variety of skills, which he's going to present right here. So, by the way, he's been with us here at the Code Dive since the edition 1, and this is what he looked like back then. So that's Andrzej at the first edition. This is Andrzej today, but we know he's not going to stop at this edition, so this is what Andrzej is going to look like at his last Code Dive edition. So please wish him good luck presenting right here. Let's plug in, let's power up Andrzej. Here comes Andrzej Krzemieński. Please make some noise.
Thank you. Thank you. So welcome after the lunch break. Thank you for choosing this talk. Contract assertions. They are likely going to be a language feature in C++ 26. So in this talk, we are going to see how they fit into the safety, security, correctness landscape. So you will hear again about these terms. from my perspective. Then we will see what contract assertions look like, how to use them, why to use them. We will see what surprises await you when you start using them, and we'll see some design challenges with the feature. So let's go with safety and security first. Safety, Timur already said that they have multiple meanings, but safety in our context will be like this functional safety. Tries to answer the question, can my product cause unintended harm? While security tries to answer the question, can my product be misused by an enemy to cause unintended harm? They are very similar in a way. They both talk about products, not language features or language, about the end products. Language safety is of interest to us only in as much as it contributes to our product's safety. They both talk about causing harm, the unintended harm, because intended harm is okay. If I'm designing a weapon, that is the whole point of doing harm. But we need to be in control. The difference is that in the case of safety, what we are fighting against is the nature and its randomness. While in the case of security, we are fighting against an intelligent enemy, human, maybe the entire country that has intelligence, resources, and determination to misuse our program. So this causes us to respond and think differently in those terms. For instance, the Swiss cheese technique would work for functional safety. This is a technique which observes that any safety measure that we take has flaws, like a slice of cheese has holes. So it's good. We apply them. Let's suppose we will be squeezing the bugs with the slices of cheese. We will remove a lot of them, but not all. But it's okay because we will apply a lot of those hole-ridden techniques. And if we apply enough of those cheese slices, we can be confident that we've covered enough of the spectrum and we achieve the desired level of safety, because it's always levels. It wouldn't work for security because of the intelligence that observes our actions and works in response to them. So whatever technique we apply, our attackers will find the holes. We apply more of those techniques, the attackers will find more holes, and even if we think we have covered the entire spectrum, they will be able to find a place to sneak in. So there are differences, but there's many levels of safety, of dealing with safety and security, and in this talk we will be only talking about one level, that is at the level of the language. And at this level, both system safety and security boil down to the same questions. The first one is, how easy does the language make it for the programmer to implement the unintended behavior? And this is the first class approach, we could call it. If the language can provide that is splendid. If it's not possible, the other question is, how easy is it to spot in the language that the programmer has planted unintended behavior? And we can call it, and we'll be calling it the second class approach to safety and security. And this is mostly what C++ preoccupies itself with. So let's see how this maps onto a bit of code. Suppose that we are investigating an incident in production. And we go back to our code because our application misbehaved. And we are trying to answer the question, regarding this function. The function just initializes some object result to 0, then it initializes or creates, because there's no values yet, some array, it fills the array, but it returns back this result object. And we are trying to answer the question, is it possible in any circumstances that the return value will be anything else than 0? I hear yes, but how is it possible? It is not, maybe one remark, it is not a global. Here we have return, so it has to be a local scope. And the rules of C++ tells us that in order to modify the value of a variable, you either have to apply an operator to it directly, like assignment or increment, or you have to pass it to another function by reference. Neither of those are happening. So C++ tells us that it's not possible. But of course, I wouldn't be showing this example if it was so simple. And if we look at the implementation of function fill, it fills the array with ones. Sort of, but I have a bug in it. And it assigns 1 not only to all the 7 elements of the array, but also to the one passed. And it so happens that on my compiler or on my architecture in my machine, this variable result has been positioned or put exactly in the place where this hypothetical 8th element of the array would have been located. So when I'm assigning to this one past the end element of the array, I'm assigning a new value to object result. And the sad or disturbing thing about this is that from looking at this code, like observing just this source file, looking at the pull request, which only has these changes, I will never figure out that this is the case. It's a remote part of my program that causes this part to behave against the C++ rules. If I put const here to indicate that this value never changes, it wouldn't change a thing. It would still be the same problem, because const tells us how C++ behaves. But once we started assigning to the non-existent array elements, we are no longer in the realm of C++, and C++ rules no longer apply. This is why we put so much attention to undefined behavior, because it prevents us from reasoning what our program does from looking at the source code. Programs like binary instructions, assembly, never have undefined behavior. They have always good, well-defined behavior. You can look at the assembly and it does something. But you cannot see it from looking at the source code. This connection between what the source code describes and what really happens is no longer there. Hackers, enemies who observe the binary know what happened, and they can use it to their advantage. But if we look at the source code, we don't see it. We are now blind. So the whole point of having a high-level programming language is so that you don't have to think in terms of assembly, but be relieved of it because you have the language. But now we've broken this link. Now the language doesn't help us anymore. And now the other concept, correctness. We start with some intentions as to what our program will be doing, but when we have delivered it, it is something else. Ideally, there is a huge overlap between them, but there are still things that we never intended. And we could even call them features. This program has some functionality. Somebody may use it. Usually it's something we don't want, something bad, but it's there. We delivered something else. We delivered some functionalities that we never intended. And A subset of those are these that trigger the undefined behavior, and in those cases, we don't know what they do. In the other case, the upper ones, they're unintended, but we can look at the source code and figure out, okay, this is dangerous, this is not dangerous, okay, we can fix this, we cannot fix this. But this black hole, this blind spot, we cannot even reason if the functionality there is dangerous or not. We don't know. Any tool that works based on language, like unit tests. In order for unit tests to work, you need to we all need to understand the language and abide by it. Can do something about the bug. In case of the blind spot, no tool that is based on the language will work. Everything unintended is a potential safety and security issues, but we have means of addressing them, like testing. For those, this is called language safety issues. We have very little tools to actually deal with it, assess the danger, assess the consequences. What we can do about it? One approach to the unintended behavior is to try to reduce it. And this is what correctness deals with. Another approach is accept the fact that our programs are incorrect, that they will always be doing things we did not intend, but try to minimize the blind spot. Let's have equal game with equal chances with our attackers, with nature, so that we can see what's going on. And this is what language safety deals with. Those are two different orthogonal goals. And the strange thing that happens, and very controversial, is sometimes in pursuit of this language safety, people will compromise correctness. And this is, okay, you gain something, you gain language safety, but it is controversial whether it is actually a thing that you should be happy with. And let's see how this works in code. Imagine that we have a program that will be parsing a file, getting some names from it, finding the best name, and doing something with it. So we are starting with two variables, file name, something that we have initially, we'll be processing this file, and the found name. This will represent one of the names that we have found. We don't have it just yet, so it will be 0 initialized. We are parsing the file, getting names, and then from those names we are getting the one that we want. There are both const char stars, the usual way of representing strings in C and C++. And another thing here, our function parse file doesn't take const char star. It takes my string implementation, which is maybe I've written it before we had std strings. Maybe there was another reason. I have my custom implementation of a string, which has a constructor. The constructor takes const char star, and it assumes that the const char star, it's not really about pointers, it's about representing a string, so a pointer to an array of characters, and because of this assumption, I shamelessly dereference it as the first operation in my constructor. Now, when I run this program through a static analyzer, like Clang static analyzer, I get this report. It's a screen full, but for a report from an analyzer, it's really short, actually. And it tells me, hey, you are initializing some pointer to null value, and then you are dereferencing it in that place. And you couldn't possibly mean that. The static analyzer, you know what the problem the static analyzers and compilers are facing when reporting warnings? They cannot give you false, they can give you false positives, but they don't want to, because if they give you too much false positives, you will just start ignoring all of this rubbish. So they have to make sure that the message they give you is a genuine bug. And here, the static analyzer decided that it is certain, it is safe to give me a good warning, because it works on a contract that everyone understands, every programmer, every tool vendor, that this is never the programmer's intention to trigger the undefined behavior. And because it has found one, it is sure that I'm doing something in this program against my intentions. The static analyzer doesn't know what's wrong, doesn't know what the bug is. It only found a symptom, but this is enough to give me a report. And now I can go back to my code with all this information and see more in a more focused way that I have passed the wrong pointer to my function. It was supposed to be file name, it's found name, because the names were so similar. Maybe the IntelliSense give me this hint incorrectly. Maybe I clicked incorrectly. Now it looks good because it's the same letter. Maybe it's ChatGPT that suggested this code. You will never see it later in the review. But now, static analyzer, which doesn't understand what the bug is, but has found a symptom, has told me that, and I have an opportunity to fix it before the program is run for the first time. The word is saved. But consider what happens if my implementation of the constructor looked differently. If I put this defensive if statement there. Maybe I shouldn't use defense if statement, because it also has different meaning to different people. But I put something that I considered a best practice. I put a check, and if it is a null pointer, I'm throwing an exception because I want to prevent the undefined behavior from happening. The moment I did this, my static analyzer ceased reporting any errors, because it has now no undefined behavior to hook to. It will not be risking giving me false positives, so it has to keep silent. I am no longer able to detect bug with a static analysis, only because I chose to protect against UB at runtime. Because there are two sides to undefined behavior. Actually, dereferencing a pointer without checking if it's null, it's not undefined behavior. Undefined behavior is a property of runtime execution, not of code. It's just potential to get undefined behavior. And true, when I combine it with a bug in my program and I run this program, only then do I get the undefined behavior. But there is also the other side of this story. If I have this potential for undefined behavior, and I have a bug, and I run it through static analyzer, I have a chance, not certainty, but chance of finding a bug, of getting a good bug report. And this is this second-class approach to safety and security. However perverse this may seem, UB can help safety and security. Of course, I don't encourage you to plant UB like that, but this observation should be kept in mind. What if I took a std string rather than rolling my own? The specification of std string, everyone can access it. It's available in CPP reference, or tells us that this is undefined behavior if you pass me a null pointer to a constructor. So when I tested this with this example with std string in my Clang static analyzer a couple of years ago, it was silent for the same reason as before. It was silent because the implementers of std string decided they would put an if statement, because they can. If it's UB, you cannot expect anything, you cannot complain about anything, you cannot complain that they put this if statement and a throw. But because of that, they silence my static analyzer. But when I run the same program through the Clang Static Analyzer this year, it did report a bug, a potential bug, because it learned how to recognize string. There is no undefined behavior now in the language level, but the tool learned how to learn std string, because std string is so popular. I mean, it's official that everyone knows its contract. And because of that, when I'm using std string, I get the best of both worlds. That is, I get the static analysis, and I get the runtime prevention of undefined behavior. And this is because the std string is special. And now with contract assertions, which we'll see in a moment, every type, your type, can be made special. Because while correctness in general is often defined as our program matching the specification, contract assertions are bits of this specification that you can put into your program, in your function declarations. And with this, every tool in the world can make use of this information the same way as Clang Static Analyzer made use of the std strings contract. Before we go to seeing the first declaration, let's look at the motivation for contract assertions from another point of view, from the source code. This is an example of a function in a program that needs to compute the total weight over all items that we have in a vector. So we'll iterate over this, nothing special, except one thing. In every programmer's head, a red light appears, lit immediately when we see this arrow sign. We are dereferencing a pointer. And the question that just begs the answer here, what if this pointer is null? And there are many answers to this question, but the first thing to observe that we have this tension. We need to make sure that our implementation and whoever calls us, we have the same understanding of what's going on. Is null pointer allowed? Maybe it is allowed. Maybe it means that in this case you use the default value or use 0 value. Or maybe it's not allowed. Maybe it's a bug in our caller. There is a tension and a need to make it clear to everyone which it is of the two. Now, before we go further with this example, let's look at another one. We have a function that checks if a given value that you pass us is in range. And range not like std ranges, but range like in mathematical sense. And is represented here by the lower bound and the upper bound, this low and high. And we apply simple mathematical formula for checking if the value is in range. There is no red light here, because we are not dereferencing any pointers. We are not causing undefined behavior. But we should ask a similar question. What if low is greater than high in this example? Why would anyone in the world call this function and pass us low greater than high if the point of this function is to check if something is in range? If you give us low greater than high, there is no range to talk about. So what do you expect of this function? And the safe answer, this is the only context where I use word safe, is that our caller, if they do that, they have a bug. They are doing it unintentionally. We are covered. We will be okay with that. We will just produce rubbish for rubbish. But our caller definitely is no longer in control of what they are doing. And we have a chance to tell them and somehow to respond. We don't know what the caller is doing exactly, but we know, we can safely assume that they are doing something wrong. In the previous case, a very clever static analyzer that sees across function invocations could deduce that you have this undefined behavior and you are not doing it right. And maybe it would even issue a warning if there was a null pointer. In this case, there is no amount of intelligence you can put in the static analyzer that would detect a bug here, because there is no undefined behavior to hook to, but on the other hand, there is our knowledge. We know the function name, we know the intention that we had when implementing this function, and this is this additional information that could be a very valuable input to the static analyzer. And this is what we are going to give it. Let's recap this part. The motivation for contract assertions is not for preventing undefined behavior. Sure, you can use it for that. You get it as a bonus, but this is not the main point. The main point is to communicate, and in a formal way that every tool in the world understands, what program states are considered incorrect at given times. So let's see how it works. This is the first contract assertions that we see in this talk. Our function in range has a precondition. We recognize it by this context-sensitive keyword pre, and we have a predicate that tells something about function parameters. It is present in the declaration. This is something new. This is something we didn't have with stud assertions. So it is in the place where the callers call us, they can also see this precondition, all the relevant information that is needed for producing diagnostics. It applies because different contract assertions apply to different points in time in our program execution. This one, the precondition, applies just before executing the function, after the function parameters have been initialized and when the function is about to be called. And what does it tell us? It tells us that if at this point the predicate that we see would be evaluated, it will not be evaluated. Well, it may be evaluated. It may not. It doesn't matter. You can control actually what happens, whether it's evaluated or not. But the point is, if it were to be evaluated, because static analyzer only do this what if, they not execute the code. So if this precondition were to be evaluated, and if it returned false, we can be 100% sure that there is a bug somewhere in the code. We don't know where, at which location, what it is. Maybe it's a bug in the predicate, but we can be sure that there is a bug somewhere. We have found the symptom, not the root cause, the symptom. And in contrast, if it evaluated to true, we can conclude nothing about correctness. Maybe it's correct, maybe it's not correct, we don't know. But when it's false, 100% there is a bug somewhere. And if we have it, if we get preconditions and postconditions, those assertions, pre and post, those precondition assertions in the language, and if you users and library vendors start to put those preconditions, we can immediately get value from them, not even using static analyzers, even using as simple tools are IDEs. Imagine this hypothetical situation that we have our function in range with a precondition assertion. We are using it in our IDE. So we get min max from somewhere, from some configuration. We pass it to our function, and our IDE helps us. It displays a hint. It knows that there is a precondition assertion there, so it prints it here. But in order to make it convenient for us, it doesn't use function parameter names. It uses the names that are visible in the scope that we are now changing. So the function arguments. So it remapped the names of the parameters, and our hint is when you call this function, just make sure that the input is less than min. And there is something wrong with it, yeah, because the whole point of calling this function is to actually check where the input is located relative to min and max. So something is wrong. Why would you expect me input to be less than min? So if I'm alerted, and now I am, I need to check. I look at the precondition. I look at the function arguments here, and yes, I have a bug. I have confused the order of arguments, and I pass them in the wrong way. My IDE detected that. I mean, it didn't detect it. It showed me a hint. It alerted me, and I actually found that a bug, but owing to those precondition assertions, the bug is prevented and fixed before the program is even compiled. So this is this. We get this left shift. The bugs are fixed earlier in the game. You don't have to wait for tests, unit tests, integration tests. You get the bug fixed immediately before you even compile the program. Another example. Suppose we are getting this min and max from the command line, from the user input in general. And now we are passing them in the correct order. And the IDE, not even Clang, not even static analyzer, just a regular IDE can immediately give us a warning. You couldn't possibly mean that. Your function has a precondition. It doesn't accept just any input. You have to make sure that some condition is in place, and you never checked it. You just got whatever your user gave you, and you just dumped it on this function. This is how bugs occur. Our user is not obliged to respect the precondition, even if you type it in the box, that just type min and max. Our user can be a hacker, our enemy, and can purposely put us wrong arguments. We are obliged to validate our input. Preconditions are not for validating input, that's for sure. And it's clear, because there is a precondition assertion, it's clear that this function has a precondition, it's clear that you didn't make any input sanitization, we can safely give you a warning. And a more complex example for this, you would need a static analyzer. If we code, our code looks like this. We check if A is negative and log something or do something else, and then we just pass 0 and A. A static analyzer can immediately give us a warning. Either you are concerned that A is negative or you're not. If this concern is legitimate, you should have checked it also when passing this function to passing those arguments to the function in range. If you are sure it's not A is never negative, because you may be sure for other reasons, because you know all your code, why are you checking it up there? Just one of those is wrong. The analyzer doesn't know which one, but it is sure that one of them is, and it can alert you and catch your attention, and the bug is fixed. So again, while assertions can be used to change the behavior of our program, because you can enable them or disable them, the runtime checks, I will not even be talking about it. It's useful, you will use it, but it's not the most interesting part here. The whole point, the main point is not about producing or changing how your binaries behave. The most beneficial part is for enabling correctness verification by various tools. You do not even need to know what those tools are. Maybe you will be writing a library. You will be putting it in your functions, and it will be your users that will consume those contract assertions. They will have the tools you have never dreamt of. And you will be, and this is the point, you are putting those assertions for someone else, so that their tools can work. And sometimes there is a need to control the tools, like selectively evaluate only some of the contract assertions, and for that you have attributes. So if we go back to our function total weight that we have, if we have precondition assertions in place, we have a number of options. We can communicate to our callers that there is a precondition there, that you cannot pass null pointers there. And then it's clear that it is the caller that is responsible for doing that. And the caller sees it from just looking at the declaration in the IDE, it's now all official. Or you can make a different decision and say that I want null pointers. They have special meaning in my program. They mean use the default weight. In that case, you will just type pre-true. Means we never report any incorrect usage of this function. The difference between this pre-true and not having a pre at all is that with pre-true, you are saying that you are doing this consciously. I've considered it, and I'm specifically sending a message that null pointers are okay, and I am in charge of handling them, not my callers. Let's look at another one, the post condition. We recognize it by a different context-sensitive keyword. Again, it has a predicate, but this time the predicate tells us about the return value also. So there is a way to introduce the name of the return value with this colon syntax. And the first thing you will observe when declaring a post condition like this one, that it does not compile. And this is very unfortunate, disturbing, but let me show you that why we had to do it. It is possible that our function select apparently you give us a range and we select a number from this range. Maybe implement it like this. That is, we iterate over the range and based on some condition change the answer that we are about to return. But as an iterator, we use this object low, a function parameter. Not everyone knows about it, but in C and C++, function parameters are just objects, at least those that are passed by value. They are not like function parameters in mathematics when we talk about values. They are just objects. Our caller initializes them, and we can do whatever we please with those objects. The consequence is that if somebody calls our function with values 1 and 10, when we are at the end, when we are about to return from this function, our ans, the thing that will be returned is 1, so fits within range. This is something that our caller wanted. But if we were to evaluate the post condition now, our low is 11. This low high is not even a range anymore. It was a range when we called this function, where the precondition was supposed to hold. So it was okay. The contract between the caller and the callee was okay at this point. But now this value is different. And for sure, our caller never intended us to check if the answer is in this 11 and 10 range. It's not even a range anymore. Our caller looks like this. Yeah? So the answer that they want is this I between 1 and 10. And we cannot compute it because we don't have the original value of function parameters. This is why we would rather refuse to compile the program than put you into this trouble of giving the false positive or false negative answers. Because this is one of the design criteria for contract annotations. They have to have the same meaning when looked at from the caller's perspective and the callee's perspective. What you can do when you pass function parameters to functions by value is to put cons there. This is nothing new. You can always do. You were always able to do that, but it is awkward. Yeah. So nobody. Well, some people do it for different reasons. But now, if you use the post conditions that reference function parameters that happen to be passed by value, you will have to do that. And this is for contract assertions not to lie. And then we are sure that the value at the beginning of the function parameters is the same as at the end. So sorry about that, but the other outcome, if we allowed it to do, would be worse. Now, post condition applies when the function returns control to the caller, not when the function body has finished executing. Remember that in C++ 20 and on, we have coroutines. And a coroutine can return control to the caller while it still has a lot of body to execute. So these two are different, and we should remember that. When a post condition is applied to a coroutine, it means it applies when the coroutine returns for the first time, and the only time for that matter, control to the caller. The post condition is expected to hold only when the preconditions hold. Consider our function. If you pass us low greater than high, it's not a range. So the question whether the result is or is not in range doesn't even make sense. And the third, maybe the most interesting and important one, post condition does not apply when the function ends in throwing an exception. It's obvious if you think about it. Post conditions are a guarantee given to the caller. Why does the caller need this guarantee of post conditions? This is because most likely it will be used to satisfy the precondition of the function that follows. Post conditions are all about preconditions. And if we throw, our caller will do nothing else because they will be killed. This is how stack unwinding works. We just cancel all the operations or our callers. So nobody will observe this value. Nobody will be interested in the post condition because everyone interested will be gone. And this is generally a contract for every function, whether we have contract assertions or not. We overpromise with our functions. When you have a function that tells you that it will get you the number of employees from a database, come on, you cannot be serious. There's so many things that can go wrong. You can lose the connection with the database. Maybe you will not have access to it. Maybe the table does not exist. You cannot promise that. So we all understand that it's just a metaphor. Right? We are just saying, we will try to get you the data, or we will say, an apology message. It's always this either or. Either the contract is, either what we promised is delivered, and this means the post condition holds, or we are killing you. Yeah, you are cancelled, so you will not complain, yeah, because you're no longer there. We could put it the other way around and say the whole and the only purpose of throwing is to communicating that we will not be satisfying the post condition. And it's always been there. Contract assertions are new, but contracts have been always there. And exceptions have always been for communicating that you will not be satisfying the post conditions. But what if you are working in an environment or in a company that bans exceptions altogether? In that case, you will need to figure out another mean of communicating failures of our function. Maybe you will use this compound return value. Result int is something from my library. It's like this stood expected. It's either int or a reason why you don't have one. And in that case, the post condition will get more complicated. Yeah? We will get implication. There will be a lot of implications when you will be using this compound, when you will not be using exceptions. It's if you have an error, then okay, you're fine. If you don't have an error, you need to satisfy this meat of the post condition. Or alternatively, if you return errors by the function output argument, yeah, you would have, because it has this conversion to bool the other way, the implication will turn into disjunction, but you will still get this more complicated post condition. And it's always the case when you cannot afford to use exceptions. You get weaker post conditions, whether you express them with assertions or not, it doesn't matter. You get weaker class invariants, weakened contracts, weakened everything, and then you have to put a lot of if statements in your code. This is why we actually would like everyone to use exceptions if possible. You will not be able to use contract assertions on virtual functions. For now, in C++26. Not because they are not useful. Everyone agrees that they should be there, but people don't agree on what they should do or represent. This is why we have still one controversy to resolve, and we could either withhold contract assertions for the next 3 years or give you them now without virtual function support, and we chose the latter. This is because we have two competing models for what contract assertions on virtual functions would do. One is that when you override a function, it shall have identical contract. And the other says the opposite, that the contract of the overriding function should be allowed to be different. And the first model is easier to teach and learn. The second model is the one that works in practice. And it works in practice because when you learn C++ from a book or in a simple class, you declare the base class, you declare the derived class, you are in control of everything. But this is not the case in reality. The reality, at least part of the reality, looks like this. The library author needs to operate with user-defined tools. Let's call them tools. The library doesn't know what tools it will be dealing with, so it has to create an interface in the object-oriented sense. There will be a tool, it has a function process, the process has a precondition, like here x and y need to be in range. And the library will come with, say, a set of algorithms that will operate with user-defined tools via this interface. The user will override this, provide the derived class. But in my tool, it's special. The library couldn't know about it because it couldn't know about every tool in the world. But my tool is special. You have to calibrate it before it starts to pretending being a tool. So it has two preconditions. Yeah, one is that the numbers need to be in order. The other that you need to have calibrated the tool. So this shows you why I need to have them different. And it's okay as far as correctness is concerned, because I will be using it like this. I will be creating my tool in my application. I will be calibrating it. I will be managing my part of the contract. And then I will be passing it to the library. And the library will only need to manage the other part of the contract, the one of the interface. So the theory works here. It's just the object-oriented design cannot reflect this. Because the substitutability in the Liskov sense that is needed is a property actually of state, not of the types. My tool is replaceable, is substitutable for the interface after you calibrated it, but not before. And the object-oriented world cannot model this. So this is why maybe we will need to have two contracts, different in the base class, different in a derived class, check both when you call my tool via the interface, and checked only the derived class contract when you call my tool directly. What you can do instead in C++26 is to apply this private virtual scheme or approach. It's available even today, but hardly anyone uses it. It is you separate the interface of your base class into virtual functions that are private and can only be overridden but not called. You can override private virtual functions. And what is exposed to the callers is the public but non-virtual interface. And obviously this public interface calls this private interface under the hood. What you get, you do it for different purposes, but what you get as a bonus that your public interface is non-virtual and you can safely express the precondition and postcondition assertions. So we've talked about one property or design criteria for the contract assertions, that they need to represent the same thing in the caller. In the Kali, there are more. They cannot affect the type of anything. They cannot affect the overload resolution. You should be able to safely add a new contract assertions to your code and not be afraid that you will change the behavior of the program. For this reason, we will not be able to give you contract assertions on pointers or function wrappers? Because we would have to somehow place those annotations in a type. So we would either affect the type or we would affect the value, and we cannot afford to do either to preserve our guarantees. What will work though is that when you have a pointer to function, obviously without annotations, you can assign it a function that has contract assertions. And when you call this function via the pointers, the preconditions and postconditions expressed with those assertions still apply. So if you have runtime checking, it will still work well, even if you call this function via pointer or via a function wrapper. Next, consider this example. I need to check if my error code that I will be assigning to is empty at the beginning. I have a bug here. I'm assigning rather than checking for equality. It will not compile because inside contract assertions in those predicates, every variable that you see gets immediately the top level const. So here I would be assigning to a const object which will not work, and I get a compiler error. This prevents a number of bugs, but not all, because you can still modify the state of your program via side effects. And about the side effects, you should remember that the predicates that you put there may be invoked, may not be invoked. You never know. So you have to design your predicates so that whether the predicates are invoked or not does not affect the semantics of your program. They cannot have side effects because you would get different behaviors. Sometimes it's possible that the predicate will be even called twice. So make sure that either you don't have side effects, or if you need to have them, that they don't affect the logic of a program. For instance, logging is one such side effect that doesn't affect what your program does. And we didn't pay much attention to it because it's the least interesting one, the contract assert, a statement that you can put inside your function body with similar meaning that this must be true at this point. Must in the sense that if it's not true, if it's false, you have a confirmed bug. So this is a summary. This is a feature, likely feature. We don't know the future, but most probably we'll get them in C++26. They are for communicating the specification. They can be enabled, disabled, probably by the compiler switch. And the predicates are regular C++, almost regular C++ code, because we've seen the const thing. So the short advice that I could give you for the end: do document your code with contract assertions, your functions, even if you don't see immediate application for it, because it is for someone else also, for tools, for your users. And do not rely on your assertions being there or doing something. They are not for doing something. They are not for making your code safer on their own. They are not for making your code more correct. They are only for exposing what is incorrect in your program. So you code as if they were not there. And plus, it's not 26 yet, but you can test it already, because test versions of the Clang and GCC compilers already have them implemented, sponsored by Bloomberg. So you can try, you don't even have to download anything, you can try it online with Compiler Explorer. Just make sure that you use these tags when you select the compiler. And that's it. Thank you for listening.
Yeah, the applause is fully deserved. Actually, the repeating of the applause always makes it even better for the presenter. So,
Thank you.
Thank you, Andrzej. Are you open for the Q&A session right now?
It looks like we have 2 minutes.
Yeah, 2 minutes is still good. So if there's anyone inside the room, of course, we can see one person. So the microphone is already passed on by Rafał. So thank you so much.
Hey, Andrzej. You mentioned that it's not currently possible to use those pre and post conditions on virtual methods. What about templates, function templates, class templates, and specializations of those?
Usually with templates. Template is no code. It will just be used to generate the code. So it's okay. You can put it. You can put your assertions there in function templates, and you don't know what happens. When you instantiate the code, only then do you know what happens. If it turns out to be a normal function, you're good. If it turns out that you've instantiated a member function of a class with virtual functions, you're not good. Then you will get an error. But generally for templates that don't deal with virtual functions, you can use them. Yeah, generally, now the question is about the specialization. What happens? Specialization is actually a different function. So you can start anew and not provide contract assertions there or provide different ones.
Thank you.
A question from the room. Just a kind reminder to all of our viewers all over the world who have decided to join us today. There is an opportunity to ask these questions also online. They don't need to be answered right now. They can be later. But if there is any question online, we would probably read that by using Rafał's mouth. So
yes, unfortunately, we don't have any question right now.
Just checking, just having a check-up on that. Just looking around the room, if there's anyone else who would like to... Oh, actually, we have two of people. So maybe the gentleman right here first, in the cap. Yeah, okay, so Tomek is here. Good, thank you.
Hi, my question is, you said that post-condition can assume that preconditions already hold.
Yeah.
And we've seen that you can have multiple preconditions. Can second precondition assume that first precondition holds, even if we only observe and not enforce? Or the second precondition cannot assume that first holds?
So this is a very good question. It opens a can of worms. You get the guarantee that they're evaluated in order in which they appear. If you evaluate them for the purpose of terminating the program when they fail, you get this guarantee that you say. If you observe them, you don't have this guarantee. In this sense, object observe, I don't know if everyone knows this mode observe. This is where we evaluate the precondition. If it's false, we are logging it, but otherwise we are moving on. In this way, we will move on to the next precondition, and it will probably, if it depends on the previous one, it will blow up.
Okay, thanks.
Thank you for answering. Colleagues, we need to park for now. Still, I hope you'll be available just to maybe answer the questions offline somewhere here in the corridors, especially that we have a nice surprise for you. Your bodies can move once again. So short break between right now and 15:05, so 3:05. It's time for you, but I want to thank Andrzej, and please do with me. Thank you so much for the presentation. Thank you.
Thank you.